Hello, I'm Steve Ruggiero, and today I'm talking about coupling the mechanisms of diabetic kidney disease by modeling the tissues of the glomerulus. Diabetic kidney disease progression is characterized by changes to the tissues of the glomerulus, the initial site of filtration for urine inside of the kidney. Some important structures to note are the podocytes, these cells in the Bowman space in yellow, and their foot processes, the smaller yellow portions. This purple membrane, the glomerular basement membrane, the capillaries, and the mesangium. Some changes that occur in diabetic kidney disease progression include swelling of the extracellular matrix inside the mesangium, thickening of the glomerular basement membrane, and podocyte death and effacement. Effacement being the process where the foot processes start to peel off of the glomerular basement membrane and fall off completely. These lead to the clinical marker of diabetic kidney disease, albuminuria, which is presence of albumin in the urine. Our research focuses on a small area including the mesangium, glomerular basement membrane, and foot processes right next to a blood vessel. And we wanted to look at the crosstalk between cells inside the glomerulus. So our podocyte model looks at the renin-angiotensin system inside the podocytes, and it includes angiotensinogen, or AGT, angiotensin 1, angiotensin 2, and renin. Elevated levels of glucose cause dysregulation inside the system at 3 separate points. For mesangial cells, we use the same renin-angiotensin system and added in dynamics for TGF-beta and MMP, or colloquially known as collagenase. TGF-beta is found inside the foot processes, but is known not to be produced by them. And so we wanted to see how TGF-beta can move from the mesangial cells to the podocytes. And also, MMP is the primary enzyme that breaks down the extracellular matrix in the mesangium, and evidence suggests that downregulation of MMP is what causes the swelling in the mesangium. We sought to use 3 different types of models to capture different aspects of the glomerulus, including intercellular biochemical networks using ODEs, a tissue structure model using an agent-based model, and a intercellular molecular transport model using PDEs. I'd like to talk about the tissue structure model first. So why do we want an agent-based model? Well, tissue is a phenomenon that emerges from the interactions of individual cells. Agent-based models are good at modeling the behavior of individuals, agents, and seeing what phenomena emerges from the interactions of multiple individuals. Our agent-based model of choice is CompuCell 3D, and this is an example of a simulation initial configuration in one of our runs. After setting up our CompuCell 3D simulation, we looked at molecular transport next. And we started developing our PDEs from a mass balance with a transient term on the left, and on the right a diffusion term and a convection term. Let's look at that velocity first. To figure out the velocity inside the tissue, we did a CFD simulation using star CCM, and we looked at the Bowman space, which we modeled using Navier-Stokes assuming laminar flow. And in the mesangium and glomerular basement membrane, we used Darcy's law, which is good for modeling flow through a porous media. This is the fluid velocity we got from our simulation. A few characteristics to note. On the left-hand side of the mesangium, the bottom region, that's where the mesangium contacts the capillary. On the right, we have a symmetry plane. So the slowing of velocity is due to these 2 converging flows that end up just getting pushed upwards. The x velocity zeroes out and only has a y component. The second is the channeling that you can see in the glomerular basement membrane. This is due to the fact that the podocytes themselves block flow and only allow flow through small gaps. We extracted the X and Y velocity fields and imported them into our CompuCell 3D simulation. The artifacting that you can see in this top image is due to differences in the mesh sizing versus the pixel sizes used in CompuCell 3D. To account for the filtering effect of the glomerular basement membrane, we added a convective hindrance, or this KC term. And what we did was we set KC to be 0 everywhere where there's the glomerular basement membrane, seen in blue. And this means that solids can only move through diffusive transport while in the glomerular basement membrane. All convective transport is blocked. Speaking of diffusive transport, for our diffusion coefficient for our proteins, we use a tool called HydroPro, which recreates a geometric model of the protein using a structure file and simulates the interaction between that model and the bulk fluid. Additionally, we added a KD term to capture diffusive hindrance due to the interactions between the porous media and the solutes. With our molecular transport equations set up, we looked at a couple in our intracellular biochemical networks next. And for the mesangial cell model, we did that by using it to define the boundary condition at the bottom of our simulation. We assumed that was where our simulation space contacted a mesangial cell. And what we did was, for each pixel along the bottom of our simulation, we instantiated a copy of this mesangial cell model 255 times. Each individual copy is associated with a face along the bottom, and we fed that model the glucose concentration at the pixel right above it. We time-step the mesangial cell models, and for the PD, when we time-step it, we fix the concentration at the bottom boundary based off of those mesangial cell models. So we end up with a gradient along the boundary condition on the bottom that is dependent on the glucose gradient right at the bottom of the simulation space. For our podocyte model, we initially tried to keep it in its own separate ODE model, but for how we implemented things, it made more sense to move it into our PDEs. And we did that by adding a reaction term. However, we want our biochemical networks to occur inside the foot processes, but not in the Bowman space. The trick to having the ODE terms work only inside the foot processes is to have the parameters be a field value and have the parameters only be non-zero inside of the foot processes. Everywhere else, they're equal to 0. And we checked to see if changing how the model was implemented affected the results of it. Seen here is a comparison between the original ODE version of the model versus the PDEs with only the reaction term in there. The convection and diffusion terms were removed. Aside from a small transient before 50 hours, there was no appreciable difference between the model behaviors. We also did an analysis of the timescales of separate processes in our model. On the left, we have analysis of diffusion of glucose only, no convection. The X and Y axes are pixels along our simulation space. And the bottom left-hand side is, once again, where the mesangium contacts the blood vessel. We fed our simulation a step change of blood glucose concentration from 5 to 30. The time reported is the time it takes for that location to reach the 95% point between those two values, so roughly 29 millimolar glucose. It takes the furthest pixel of roughly 10 milliseconds to fully respond to this step change. We also looked at the intracellular biochemical networks, looking at their ODE implementation only. We fed these ODEs a step change in glucose as well, 5 to 30 as well. And angiotensin 1 and 2 react on the time scale of seconds, roughly 3 seconds for angiotensin 1 and 30 seconds for angiotensin 2. Angiotensinogen, TGF-beta, and MMP react on a time scale of hours, roughly 3 hours for TGF-beta, and hundreds of hours for MMP. Note that angiotensinogen drives a secondary response in angiotensin 1, 2, and TGF-beta, which is why there's this response after angiotensin already levels off. This is the glucose field in our simulation at a time step. We still see artifacting. That is likely due to the artifacting in the velocity field. And these are the concentration fields in our simulation. Note the concentration polarization moving from left to right in the mesangium. This agrees with prior models looking at fluid flow and solute transport inside the mesangium. We also see a concentration polarization right beneath the glomerular basement membrane. Some conclusions that can be taken away from the current state of our work is that we're able to consider the effect of space on cellular crosstalk. Tissue geometry has been coupled back into the PDEs. The KD and KC are based off of the positions of the glomerular basement membrane and mesangium, which can fluctuate. When they do move, KD and KC are updated based off their new positions. And we also built a framework for connecting models of DKD progression to progress the glomerulus tissue from a healthy state to a disease state. That is it for me. I'll be available during the Q&A time slot for this presentation. I'll be there if you have any questions for me. Thank you and have a good one.